Let's talk about password cracking. For simplicity, you can consider it to be 3 ways to crack passwords. First, you've got dictionary attacks. This is where you try all words from a massive dictionary of words, including especially common passwords that we use or humans use. Humans only generally actually use around 10,000 or so words anyway. So a good dictionary of common words goes quite far in helping you to crack simple passwords. Then the second type is brute force attacks. This is where you try every single password possibility using every possible character combination. And then you have hybrid attacks where you use the psychology of human behavior, combine it with a dictionary and brute force attacks. So those would roughly be the 3 main ways of cracking passwords. But then to dig into it in a little bit more detail, in the cracking world, there are many specialist types of attacks, where, as it says here, each word of a dictionary is appended to each word in a dictionary. So you can see the input here, these words, and then you combine them together in order to get passwords you can use for cracking. So that's a combinator attack. And then you can have rule-based attacks. So based on the input words from a dictionary, you design rules to produce variants of those words. So you can see here as an example, we have the input words, and then based on a rule, it will change that word that's in the dictionary and produce this output. So you can see you've got things like change it to lowercase, change it to uppercase, capitalize the first letter, the sort of things that human beings do with their passwords. And here you can see all of the rule-based derivations of the word password. You can analyze password patterns. So for example, after cracking a percentage of passwords from a site or a location, you can look for patterns, password length, character set, complexity, mask, and feed this in to refining your rules. And any good cracker will absolutely do that when they have a lot of password hashes to crack. And you would also create custom rules as well. If you know the source of the hashes, such as the famous Ashley Madison hack, you would scrape the company website to make a list of words that pertain to that specific field or business. Or you would work out what the words were yourself. For example, the crackers of Ashley Madison tried words orientated towards dating and gender, and those words did feature prevalently in the cracked passwords. You can try leet speak as well, where 3s are changed to E's and O's are changed to 0s. This is a common technique that people use. You can apply leet speak as rules on the dictionary words that you have. Markov chains can be applied to password cracking. In general, we know capital letters come at the beginning, lowercase letters come in the middle, and symbols and numbers come at the end of passwords. And attackers are able to crack almost as many passwords assigning rules like this as they are with straight brute force attacks. Cracking can be done online or it can be done offline, and this actually makes an enormous difference. Online attacks are where the cracker interacts with the crypto system, usually a dictionary attack against a network-based service. For example, SSH login or website login, and a tool in Kali, which you can see here, supports this online password cracking. And you can see here some of the syntax. So password cracking FTP, IMAP, POP3, FTP. You provide it with the list, you provide it with the password, and you can even use proxies as well. Hydra is a common tool used for online cracking. And online attacks can also be just a few guesses against an operating system login. You throw a few usernames and passwords at it and see how you get on. But online attacks are extremely slow attacks because of the response time of the crypto system. You are interacting with the crypto system as you attempt to do the cracking. And with Hydra, in this example, this will be done potentially over the internet or over a network, which can slow it down even more. So you can be in the region of, say, 1 guess a second to maybe 1,000 guesses a second, depending on the system's response time, what sort of system it is. There are many variables. And most modern crypto systems and services can defend themselves against these online active attacks because they are simply aware of the number of attempts that are being made. So if you take any of these, for example, FTP, IMAP, POP, SSH, servers that would receive this sort of attack, the sort of defense that they might have is to block the IP of the attacker once a certain number of attempts have been made. They could also maybe inform the user of an IMAP account, an email account, that something is wrong, or they could inform the administrator, and they could even lock the accounts out. And they would lock the accounts out if it was something like an operating system, if you made too many attempts to log in. So these defenses all help try to mitigate these active online attacks. And although these online attacks are common, they are only successful against very simple usernames and passwords like username admin, password. We get these sort of online attacks consistently against our servers, and that's not unusual for anyone that's on the internet. And I can even see when I look at the logs which tools they're actually using based on the traffic, because these tools give away a signature. Hydra, for example, is quite easy to tell that they're using. And of course, the usual defense is to block the IP address. The attacker then automatically changes the IP address, more than likely to proxies, especially if they're using Hydra, or they could change it because they've got a botnet, and then they keep trying to crack the login. The normal defense is then to block that IP again, and you keep doing that back and forth until they go away. And this is all automated, both sides. And with strong passwords, they're doomed never to succeed because the passwords will never be correct. And with online attacks, they just simply cannot try enough usernames and passwords to crack systems with complex passwords. So that's the online attacks, when you get to interact with the service, interact with the crypto system. And then there are the offline attacks, where the attackers have access to the password hashes. There is no interaction with the crypto system. The crypto system cannot defend itself. It is just a case of trying to convert these hashes. These are examples of hashes with the various hash types, and convert them into their actual plain text value, which you can see here as an example. This is a file of usernames and the hashed password, something that will often be within a system in order that people can log on. We talked about hashes and passwords in the crypto section, but let's revisit. Storing passwords in clear text is massively insecure. This here should never be the actual password when it is stored in a system, but people still do it. I was using a system the other day, and the admin was able to give me the password of an account, which shows that hashes are not used. This is because hashes are one-way functions. Once a password is put through a hash, it is converted to this fixed length string like this, and it cannot be converted back to its password. It can only be attempted to be cracked. This is why they are better to use than clear text passwords. The idea is if they are stolen, they still need to be cracked. If they're in plain text, then they don't need to be cracked, obviously. And in order to confirm someone's login, they either send their password and you convert it to a hash and compare it. And from the comparison, if it's the same, then you know it's the correct password. Or the user actually sends a hashed version of their password and the two hashes are compared. That is obviously the more secure version, to send a copy of the hash. And this all happens behind the scenes on many systems. And we've got a website here where we can put data or input into the web form and run it through one of these hash functions. You can see we've got all these here. So let's do it with SHA-1. Try password, hash it, and there we are. That's the hash of password using SHA-1. And for everybody who uses the word password as their password and SHA-1 is used, this will be the hash. And you can see here with SHA-1 it's quite short relatively, but if we were to use SHA-512, you can see it is much larger and therefore harder to crack. Here we have a form that enables us to enter input, and it will run it through the PBKDF2 hash algorithm, which is the password-based key derivation function number 2. So let's put in our password as password, and we'll press this. In the real world and on good systems, passwords are often concatenated with a random and non-secret value called a salt. So we see this in here. That's what this would be here. And we can change its length. So let's call it salt1. And this would be stored with the password hash. So let's hash it. And there we are. We get our hash based on this hash function. Now, because this is salted, it has been concatenated with this value. So if we change this, it would mean our hash value would be different even though our input is the same. So let's hash that, and we can see we have a different hash. So because users have different salts, it is not feasible to store tables of pre-computed hash values of common passwords called rainbow tables to make it faster to crack the passwords, which is why people salt passwords. But salts aren't quite as useful as you might imagine. Almost no one uses rainbow tables anymore in the real world when it comes to cracking anymore. This is because the file size for the tables have just become too massive and are less useful now that GPU-based cracking is possible. GPUs offer much better performance over CPU for cracking passwords. Salting does nothing to slow down the cracking of a single hash and does little to slow down attacks on a small number of hashes. When you are trying to protect a lot of passwords, say for example you're the owner of a site with many thousands of users, salts are more useful as a defense, but they are less useful than people think. This is because when you crack a large number of passwords, like for example the Ashley Madison website or other websites, or wherever they come from, a large percentage will be cracked quickly because when you have a large number of passwords, many, as is the nature of human beings, will simply be poor even if there's password policies. And then that leaves you with a shorter list of passwords. And when you have a short list of passwords, salts become less of a useful defense. Hence why salting isn't a strong mitigation to slow down cracking, but salting should still be used though. Security architects, when designing solutions for authentication who know what they're doing, use key stretching functions, also called key derivation functions, such as this one here, PBKDF2, and also bcrypt is good and scrypt is good as a key derivation function. And what they typically do is use repeated invocations or iterations of a cryptographic hash to increase the time required to perform brute force attacks on stored password digests. And this is how you want your passwords stored, not that you have preference most of the time. And with this, I can show you exactly what I mean. So what we can do here is we can give this 10,000 iterations. And what that'll do is it will take this password, it'll run it through this hashing algorithm, concatenating it with this salt value, produce its output, which is the hash key. It'll then take the hash key and run it through 10,000 iterations, or however many we decide to put in, hash, and then that gives us our hash value. So if we change this just by 1, we will still get a different hash. If the system or site you use uses a good key stretching function such as this one, and your password is complex, even if someone steals the hashes, your password will take impractically too long to crack, even with extremely powerful machines and nation states behind the cracking. One way to make hashes even more secure, and this is now getting a little bit deep in terms of the crypto, is to use another secret key to encrypt the hash while it waits in the database, ready to be potentially stolen. So we would take this hash, we would not store this. What we would do is we would make this as input to a round of encryption before we stored it. And this would be encrypted with our master password, encrypt, and then finally we have our encrypted hash, which has been salted. It's used a key stretcher, it's had 10,001 iterations, and then it's been encrypted with AES and a master password. But the trick though is where to store that master password that we've encrypted this hash with. Ideally, it would be on another server or location separate from where you store the actual resulting value, the resulting hash, if, of course, you can afford it. But the best way is using something called a hardware security module, which is what you can see here, which is where you would store the master password, or with some HSMs, they actually do the processing for you and the password doesn't leave the HSM. And these HSMs can be big old powerful expensive servers like this Talis, like you can see this rack mountable one here, or you can get little ones like this Nitro Key HSM at €50, which you could use for storing your own passwords. Or if you've got your own server, you could potentially use it as a HSM. And the second way to encrypt the hash to make it more secure is to include a secret key in the hash using a keyed hash algorithm like HMAC. So here would be the password, then we'd have the master password, and then we'd have our hash algorithm and our iterations and our salt. And there we have our resulting HMAC. Unfortunately, people, even security professionals, don't understand the nuances of password hashing in crypto. So often passwords are stored with weak hashes, and that's just the reality of the situation, and another reason why you don't really want to share your password among sites, especially not with accounts that you care about.